This paper is one of the researches of the PSRTI Research Division that aims to realize the Sustainable Development Goal number 1 of no poverty. The study contributes to providing a more frequent estimate of poverty that will aid in policymaking. This study builds upon our previous research on interpolating the poverty incidence during non-FICE years, which is forthcoming in the Statistical Journal of the International Association for Official Statistics. Our current research is a work in progress, and this presentation will show the proof of concept of our nowcasting methodology. We would also present the succeeding steps that we want to do moving forward. We would also like to know your comments and suggestions to further improve this study. The outline of the presentation is as follows. We will present the research problem, followed by the objectives of the study, an excerpt of our literature review, followed by the methodology. We will also share with you the initial outputs that include model estimates, and lastly, the next stages or steps to be done for the paper. The Philippine Statistics Authority uses an income-based approach in measuring poverty, wherein a household is classified as poor if their per capita income is below the poverty line. Poverty statistics such as the poverty incidence, poverty gap, and severity of poverty are estimated from the Family Income and Expenditure Survey, or FICE, that is done every 3 years. This means that policymakers need to wait for a substantial amount of time before they can determine the effectiveness of their poverty alleviation measures and craft new policies. The PSA also conducts the Annual Poverty Indicator Survey, or APIS, during non-FICE years. This survey has a smaller sample size than the FICE, which raises concerns about the comparability of poverty estimates between the two surveys. Although APIS gives an up-to-date snapshot of the poverty situation, conducting the APIS entails cost in terms of manpower and budget. An alternative method in estimating non-FICE poverty statistics is a model-based approach such as forecasting and nowcasting models. Nowcasting predicts the current poverty statistics using the past values of poverty and current values of explanatory variables. And this study explores the use of nowcasting in estimating poverty statistics, particularly the poverty incidence among households. Since nowcasting will use currently available data, it is less costly than conducting a full survey operation. The primary objective of this study is to generate nowcasts of poverty incidence among families. The study aims to use a factor model for the poverty incidence. The advantage of this approach is that it can be applied to a multi-frequency dataset, and this is important because the poverty incidence is collected every 3 years, while the explanatory variables available have a quarterly frequency. The use of DFM for the purpose of nowcasting and forecasting has been in various studies. Dos et al. Employed a two-step estimation of the factors in a dynamic approximate factor model of large time series datasets. The parameters for the model were estimated using the principal components analysis, and the factors were estimated by applying a Kalman smoother. We intend to also use a two-step approach. First is to extract the dynamic factors, and second is to nowcast the poverty incidence using the extracted dynamic factors. We use the state space model in both stages for more flexibility in our model specifications. This is similar to the approach done by Gerlach and Yu in 2004 in forecasting the GDP movement in Hong Kong. The study used the following variables. The variables are grouped into two: macroeconomic indicators and variables from the quarterly labor force survey. These variables are transformed to their stationary versions and standardized to have a mean of 0 and variance of 1. The standardization was applied to reduce the parameters of the factor model and for estimability. The first stage is the extraction of the dynamic factors from the quarterly economic indicators. The idea is to extract the dynamic factors alpha sub t from the set of variables in the vector y sub t. This study assumes that the movement of the economic indicators are manifestations of a set of latent dynamic factors in the economy. That is, the economic indicators are dependent on the latent dynamic factors. This assumption is justified by the following. First, the leading economic indicators are theoretical concepts of economic movement. Second, the values of the leading economic indicators are estimates, making them random variables that can be modeled. The state variable is the dynamic factor that drives the economic movement of the observed variables y sub t. Therefore, y sub t is assumed to be determined by the common component and its idiosyncratic movement epsilon t. Z sub t is the matrix of factor loadings, which can also be time varying, but in this study, we assume it to be time invariant. The covariance matrix of epsilon t, which is H, is assumed to be unconstrained to allow for cross-correlations among the variables in a particular group in y sub t. This can be modified to be diagonal, which forces all cross-correlations to be explained by the dynamic factors. Nonetheless, we use a more general assumption in our initial model. The covariance matrix of eta, which is Q, is constrained to the identity matrix, which implies that the resulting extracted dynamic factors form an orthogonal set with a variance of 1. Dummy variables are introduced to represent the periods where there is a significant change in the variable definition or estimation methodology. We add this to have a more accurate measure of the variance. The first stage model is estimated by maximizing the likelihood function using the expectation maximization or EM algorithm. The EM algorithm first gets the expected value of the log likelihood given the initial values of the parameters, where the dynamic factors are estimated using Kalman filter. The EM algorithm then updates the parameters by maximizing the log likelihood function. We achieve convergence when all parameter estimates are stable. The number of dynamic factors to be extracted was determined by an automatic search procedure using the Bootstrap AIC. The Bootstrap AIC is said to perform well given a small sample and a large or complex state space model. The confidence intervals for the parameters are also determined via bootstrapping. The second stage model relates the extracted dynamic factors to the poverty incidence. The poverty incidence is assumed to be the mean of the dynamic factors with a time-varying scaling parameter. The scaling parameter determines if the particular dynamic factor influences the poverty incidence at every time point t. The second stage model includes a local linear trend with the parameters mu and nu to take into account the possible existence of a stochastic trend in the poverty incidence, as we observe that the poverty incidence has been on a decline. In state space form, we have the measurement and state equations 1 and 2 respectively, where the covariance of the error of the state equation is diagonal. The model is again estimated using the EM algorithm. We use the mean absolute error and the mean absolute percentage error to measure the prediction performance of the first and second stage models. Since the indicators are standardized in the first stage model, the computed MAEs are in terms of 1 standard deviation. As for the stage 2 model for the poverty incidence, the MAE is computed for P sub t or the poverty incidence versus the 1 step ahead forecast, the expectation of P sub t given the information set until time t minus 1. We present the initial outputs of the study to show the modeling process until the generation of nowcasted poverty incidence. We will not interpret the results of the full model because it needs to be subjected to variable selection and other improvements. 2 DFMs were estimated, one for the macroeconomic variables and another for the LFS variables. Initial results indicate that there are 4 dynamic factors to be extracted from the macroeconomic variables and 6 factors for the LFS variables. The extracted factors are rotated for interpretability, and in this study, we use the Varimax rotation. One observation is that running a pure EM algorithm on these models takes time to converge. We observed that initializing the model parameters using MLE dramatically cuts the estimation time. Moreover, bootstrapping also takes a while to finish. This can be shortened by applying variable selection and restrictions on the covariance matrix. The next step is to input these dynamic factors to the second stage model for the poverty incidence. These are the smoothed series of the second stage model. State variables 1 and 2 are the mu and nu of the local linear trend specification, while the other state variables are the significant beta coefficients of the moving averages of the dynamic factors. It seems that the local linear trend overwhelms the extracted dynamic factors in nowcasting the poverty incidence. This implies that the poverty movement is fully determined by the trend specification. Perhaps the mean specification can be simplified to only a local linear model without the trend, and this will force the model to explain the poverty fluctuations by the dynamic factors. The output shows the one-step ahead estimates of the poverty incidence versus the actual. We have a MAPE of 3.4% and an MAE of 0.645 percentage points from the actual poverty incidence. These low error values could be due to the overfitting induced by the local linear trend model, which again will be remedied by simplifying the mean specification. The estimated model produced the following nowcasted poverty incidence. The nowcasting dataset includes observations until 2021 Q2. We note that there was no reduction in the poverty incidence during the pandemic. This is due to the earlier observation that the model gives more weight to the local linear trend part than the dynamic factor part. In summary, the initial results show that the nowcasting methodology can be operationalized, and we plan to apply the following steps. We would try to reduce the complexity of the trend component, or the mean specification, by using a local linear model instead of a local linear trend model. We would also apply variable selection to the dynamic factor model, which will improve the estimation of the dynamic factors. We are also considering to add lags of the average dynamic factors, as the macroeconomic movement may have delayed effects on the welfare of the households. We look forward to your comments and suggestions in improving this study. Thank you for listening.